Okay. Okay. In case we're not here next week, let me get you started on your first project. Hopefully these labs haven't been too bad. Y'all been okay so far? You all right? Jonah?
Couple hiccups in the timing, but
It's still fine? Yeah. All right, so let's go ahead and get started on our first project. We'll probably have to start this semester. So this will be the first one. 4 projects?
great.
Fantastic. Yeah, it is fantastic, isn't it? It's wonderful.
Not 6.
It's not 6
Happy
though,
about
so
that.
it's not amazing, but still fantastic.
More than
Okay. All right, first project. Here we go. Storing and searching based on key value pairs is very common. There are tons of times where you want key value pairs. Those of you who have worked in the industry, a lot of times you're just trying to retrieve something based on a key. Have you done that a lot, Daniel? Key value pairs?
Oh, yeah.
Oh, okay. Complex data structures exist for general purpose key value search and sort. All right, there's a lot of general purpose algorithms out there, but if given some constraints, very efficient ones can be created from simple arrays. All right, again, I'm going to say this multiple times. For this project, you just need simple arrays. You don't need to use anything advanced like a hash table or a hash map, which is a common implementation, which will actually not work in this case due to something I want you to do. So don't use a hash map. Our map shall map a student's first and last name to an ID. In other words, we're mapping a string to an integer, all right? That's your first big constraint. You are always mapping a string of characters to an integer. So I'm going to tell you this string maps to this integer, and then later I'm going to ask you certain things about it. Okay. First off, the name, or the student's name, shall be a single array of characters. It's really an array of characters. It's a combination of first and last names separated by a space. So it has only alpha characters plus a space. The first letter of each name shall be capitalized, the rest in lowercase. In between each first and last name shall be a space. Every student's name shall map to a single 32-bit integer, and all IDs should be greater than 0. Any questions so far? All right. It is imperative you think about how we can simplify this problem given constraints. The general solution will be too inefficient to solve in the given time. Here's the interface. Map. Add the key and value. Notice it's a character array to a value. When I call, and it's going to return Boolean if it's successful. It's not successful if we're out of memory or if the key exists. So if I try and add a key to something that already exists, you return false and do not overwrite that key. If you're out of memory, return false as well. If you don't have swap space enabled on your machine, you will run out of memory for some of these tests. Get searches for the key if found. It sets ret to its value and returns true, otherwise it returns false. Notice I'm doing a reference here. So if I do key, Steve Jobs, ID 1. When I do get on Steve Jobs, ret should be equal to 1 and you should return true. All right. Size? Yes.
So, the key that's being passed, that's someone's name
First and last name, separated by a space.
that is given by one character.
Given by a character array. It's an array of characters. Null terminated. Y'all did null terminated arrays in procedural? The last element, when you go through this array, the last element will be \0. That means it's the end. All right, there you go. Size returns the memory consumed by this data structure. You're going to have to figure out how to calculate that. And I will help you with that in the, if not today, in the coming slides. Removes the current value from map. It frees up any memory that it can. Returns true if there was something to remove, false otherwise. So I need to be able to remove from this map. All right. Now with just that right there, a hash map is actually a very quick implementation. With this next function, a hash map is an absolutely terrible implementation. How many returns the number of names with a given prefix. So if we have in our map John, Jonathan, Paul, Mark, Luke, and Joanna, then how many of JO would return 3? Because you have John, Jonathan, and Joanna. Okay? Everyone good with that? And of course,
Under remove.
this is just the order I put in the functions. The reason for it is I highly recommend you implement add first, you implement get, implement the size, implement remove, and then implement how many. It's my suggested order. You can do it however you want.
I was messed up. I thought that comment went with the function of remove.
Oh, no, no, no,
Makes
no.
sense now.
And then map freeze on memory. Of course, you're going to store your data under private. I highly recommend that you come and talk to me about your data structure before implementing. I expect all of you to come and talk to me about your data structure before implementing. Please, please come and talk to me. The way this pretty much always works is those who at least come and talk to me, they pass this project. Those who don't fail. Has been pretty much the consistent way it's been. So please come and talk to me. If you can't get to me, email me. Might be able to help you over email as well. But in person is going to be a whole lot better because I can help direct you to a good solution. All right, important questions. Of course, the crux of this project is determining what data structure you're going to use or what it will consist of. I provided a common list of first names and last names. Them first name. Here's a bunch of first names. Oh, look at all those. How many are there? 5,163 first names. And I've also provided last names. How many of these are there? 45,905. All right, so you have some first names and last names to play around with if you want to.
Just some?
Just some.
Yeah.
If you were to create an array of all possible combinations, it would take a little over 4.5 gigabytes.
So don't. How long would it take?
I think on my machine it takes about 3 or 4 seconds to build that list.
Really?
Yeah.
So don't.
You probably don't want to do it.
I'm just making an array of like 5 names.
Definitely start with that.
Yeah, and then like 5 numbers to go with them.
A list of all possible IDs would be just over a gigabyte for a total of 5.5 gigs of memory, which may not fit on your RAM. How much RAM do your machines have? 8.
I think I have 8.
8? Oh, 8. All right, cool. All right, good. So it fit your RAM. That's good. Awesome. But then you need to add whatever your data structure is, so that might add some additional overhead to it. So it could easily go over 8 gigabytes, by the way. With and it could still be a solid, good solution. Obviously, my test cases are not going to be for the full. Well, not the full thing, but it'll be close. I think I do for. I think go about 1/10 of that. So about a gig, a couple of gigs is how much I expect everyone to be when I use the full large data set. Keep in mind we are storing the IDs. All we care about is the ID. We don't actually, the name is just a mechanism to get to the ID. That is your first huge hint. All you actually have to store is the integer, and then you have to figure out how to go from a name to that integer. That's your first big hint. While the student's name is used to index and do an ID, how can we efficiently store the names to map to an integer? It's vital you think again of the data structure before you start coding. I suggest drawing up some pictures if you're having problems. Come to me with pictures. I love to see pictures. Boxes and arrows, beautiful. Drawings? Drawings? Sure, that'll be good. Just don't get too fancy. I might be lost and I'll be, distracted. Problem.
Get distracted. Really
Get distracted real quick. Colors, yeah. Yeah, if you do colors, oh my goodness. All right, we've learned arrays and pointers. You haven't learned linked list yet, but you are allowed to use a linked list once we talk to it if you want to. I'll tell you right now that my most efficient solution of this does not use a linked list. But that should be enough to design your data structure. No hash maps for the problems. They will not solve the prefix problem efficiently. You'll be judged on your memory footprint as well as your performance. We'll talk about your grade in a moment. Code names. I hope that we get enough people here to actually attempt this project so I can actually demonstrate the performance of basically everyone in this room versus each other. And of course, I'll throw myself up there, but you know, mainly against everyone else in this room. My policy, I'm not supposed to imply anyone's grade. So if you give me a code name that you want to go by, you know, Code Wizard, Wombat, etc., you know, code name, I will use that when displaying.
What is the 1337 from? What is
Leet.
that?
Leet. Like eat.
Yes, that's it.
Leet. All right, warning. Data structure projects are significantly more demanding than labs. Did you find that to be the case, Johan?
God, yes.
It's imperative you start thinking about the data structure now. I've given you 3 weeks for this project. Start now. If you hit a roadblock, and you should/will, I don't expect any of y'all to be absolute geniuses and get this on the first try. Please come and talk to me. Please come and talk to me. When you talk to me, be prepared to show me what you have thought of so far. If you come in with an idea, I will guide you to a good solution. If you come without an idea, I'll tell you to keep thinking about it. Keep in mind, there are many good, fair, and terrible solutions to data structure projects. There is no one solution that is there is no one solution that is good. There are many good ones. For this one, I've only found one solution that's the best. That doesn't mean there aren't any others. But there are many solutions that are good that will still give you a name for this project. Grading. All right, I'm going to try and keep this pretty straightforward. Your program will be graded first based on accuracy. If your program passes or passed my test cases, accuracy tests, then additional points will be awarded for performance. So you must first be accurate. Keep that in mind. That is the most important thing. So accuracy is the first 30. The performance of search, aka get, is 30. Performance of how many is another 30. And the last 10 is your memory footprint. I'll grade on how much memory you're taking up. All right.
So with the memory footprint, is that like how much memory is taking up by the end?
Yeah, so if I throw in 10 variables and all of a sudden your data structure takes up a gig, you're not going to get very many. You're not going to get any memory points. But if I throw in 10 things and it's a simple factor of 10 is how much data you're consuming, you get 10%. And you're accurate, you'll get a 40 right there. Plus, I'll then add points for your performance based on other things, which I'm going to get to in a moment.
So you're going to be testing. Are you when you do your test cases for this project?
Mm-hmm.
Are you going to use the whole name files you just showed? No.
But that should not matter. Really, to test this, I only need to put it at 10, and then I can test a lot of things. All right. I have generated some graphs in the objectives directory to give you an idea of performance. Please keep in mind that these are on my machine, which is an i5. If your machine is faster, you should have better performance. If your machine is slower, then you should have slower performance. On my machine, I have 8 gigs of RAM. So let's go look at those graphs real quick. Let's see. All right. So I have, let's see, we got for how many? Let's look at search first. You have search, you have 60 points and then 100 points. I'm going to show you the graphs first, and then I'm going to explain my test cases to you. So if I were to open up my search timings, 60 points, I have not completed these graphs because some of them take too long. A small search, basically I have a small data set, and how many searches am I performing? Well, I start close to 0 and go up to, looks like 25,000. And how much time does it take at 25,000? It looks like about 6. That's under a small data set. Under medium, well, I started at 10, and it just took too long. This is for a 60-point implementation. This is the performance of a 60-point implementation. So your implementation should be faster than this. If it's not, then you get a 60% of that 30% is what I'm saying. All right. On the other hand, oops, let's go close this. I think I have a 100-point version. I was not able to complete this one. I had to leave. But let's see what we got here. The small search. Yeah, notice it's 0.05 up to 0.3. The other one was going up to 6 seconds. So this one is significantly faster. I'm going to update this graph, but at least gives you an idea, especially with small and medium, about how fast it should be. And that's for a 100-point version. Obviously, if you fall somewhere in between, I'm going to award grades based on that. If you do better than this, I will take that into consideration. The next one, how many? We have a 60-point version. So this is for a very poor performer. The small number of queries up to 26. I only did up to 26. Takes just under 2 seconds. Medium, 6. And then large looks like it was taking up to 13. I started having some memory issues on large. That's why I was bouncing around. Let me see if I can iron those out on another machine. That's for the 60-point, 60% of that 30%. Let's see, we got 80. So that was going up to, what was it, 6 seconds? No, this one goes up to 1.8. On the small set, up to 0.2. You can look at these numbers as well. And then we have a 100-point. Okay. To the 10 to the negative 5. All right. This, yeah. This is the 100-point version. In other words, it should take almost no time to find this out. That should give you a huge hint, actually. Okay. Hopefully that gives you an idea about how I'm going to grade performance. I'm trying to be somewhat quantitative about it, but there is going to be a lot of qualitative attributes here. I am going to inspect your code in this one and figure out what you did performance-wise and award a grade that I believe is appropriate. But I want to at least give you something that if you did it this quickly, you are going to get this grade. To be clear, if you a hash map / hash table implementation will be issued a 0. Do not use it. If you do, your grade is a 0. You got it? It's not going to work with prefix anyways, so don't start with that implementation. But I don't want someone to get a, what is it, like a 60 or 70 because they just imported hash map and called it a day. The point of this is to be able to do both efficiently with search and how many. Tools from the standard template library, which we will start talking about soon. You may use vector, which is how they do arrays. You may use string, of course, to do strings. List, which is a linked list implementation, and of course IOStream if you wish to print. You may use any standard C library tools. There aren't really that many out there, so you're free to use them. Notice that I said standard C, so don't go and import, a BSD B-tree implementation. Use the standard C library, which does not even have linked list in it. Make sure you write test cases. They will help you immensely on getting a better grade. Add it to Git, standard way. It's due 3 months or 3 months. Whew, 3 weeks from
3 months from now.
3 weeks from today. No teamwork. Your work must be your own. Any questions so far?
So the data structures we can't do yet because we haven't worked it, correct?
You can do this right now.
Oh, we can.
With the knowledge, my best solution only uses the knowledge we have gone over today. Gone over up to today.
Okay.
There are other solutions that are good that we haven't gone over, but we are going to start talking about.
So that solution uses pointers and arrays?
Yep.
Okay.
That's
That's
all.
the best solution.
That's so far the best solution. so far. I'm not saying it's the optimal one.
I have a question. Is that date, depending on what this storm does, is that date gonna be subject to change, or?
So I'm giving you this now in case we all aren't here next week, so you can at least think about it and work on it.
Okay,
So, no.
okay.
Unless the storm happens to be a 3-week-long storm.
Okay.
Then, we got other things we can worry about. Okay. Let's go look at what I've given you so far, because I have actually given you some things. First off, I have a make file. This should look exactly the same as beforehand. This will be pretty much our standard make file moving forward. Inside of source, I have, you don't have a back directory because those are my implementations. If you do, oh no. But I do have a header file, which everything from the project already put in there. Notice that I have not filled out private. That is your job. And it looks like I have a CPP file. Great. It just returns a bunch of default stuff. Doesn't do anything. If I look in the test directory, all right, this is where things are going to get a little confusing. These 3 tests that I've created, build test, HM test, and search test, are tools in order to generate performance numbers for you. All right? They're going to generate performance numbers.
So that's what we use when we're trying to use the new plot?
Yes.
Okay.
So I've already built this part for you.
Yes.
Isn't that nice? So build test, real quickly, a lot of confusing code, but what's going on, test 1, opens up first names, opens up where it's going to store the build times, and right here it's going to read in all the first names, and then it's going to read in all the last names. It's going to close those 2 files, tell you the number of files read. Then it's going to go through a certain number of that list and try and add it to your map. And it's just taking how long does it take to create your map with that size. That's all it's doing. Build test is not really doing anything big. It's just to show you, hey, how long does it take your program to actually build this thing.
That's what we use when we're trying to.
This is just to show you how long it takes to build something with your code.
So, theoretically speaking, if I wanted to like do a graph that shows like my performance.
Build time. It's going to put the data out in build times.data under data. Data directory build times.data. Okay?
Is not data?
So if you go into data, you're going to have, oh, I already have something stored there. Oh, that's cool. So I've already done one, looks like for HM small, so let me go look at that. Oh, so that's our fast one. And what I've already done is done a, looks like an HM timing plot, so I can do data/HM timing. And then it's going to generate a PostScript file, and that is that one right
I
there.
think I see what you're saying. So we use build time, we use the output of build time, we put it to a data file.
Yeah, build time's going to automatically output it to the correct data file, and I've already created a plot file that you can do a new plot on in order to read in that data file and generate a plot for you.
So we don't have to create like that.
No, but I highly recommend you inspect what I did, because going forward, you're going to have to do it. I just wanted to give you, hey, look, this is how it's done, and then I'll, knock the training wheels off. You still have some training wheels on. It's okay.
Broken training wheels.
Broken. All right. I know reading code is annoying, but you got to do it. Search test. Notice I have small, offset, medium, large. What's going to go on, it's the same piece of code where it reads in first, last names, reads them into these vectors, and then what it's going to do is run a search test for small, medium, large. So with the search,
Modulus D mean, or modulus S?
oh, that's for printf. I'm going to print an integer right here. What integer? Whatever's returned for how many. This code is leftover code. It shouldn't be there. So what's going to happen here? Well, open up a file, put in small, medium, or large. I'm going to first build it. Then afterwards, I'm going to take timings. This is actually kind of long, but it takes timings of, let's see what we do. Doing a certain number of searches, from 0 to names, search a certain number of them. and then I'm going to take the timing and print them out. So it does that for searches, and it's going to do the same thing for how many. So you can run these tests, and it'll actually start generating the small, medium, large data set. And if you wanted to change what the size of the small, medium, large were, you just change. If you want to make it smaller, you increase these numbers, because these are the offset. AKA, with small, it's only going to add the every 10,000th element in that whole array of first and last names. The medium's only going to add every 1,000th one, and large every 50th one. There's a lot. All right. Any questions about this project? I highly recommend, remember, accuracy is the most important. Think about your data structure. Definitely come talk to me. Oops. All right. Yeah, anything else? No?
Is there gonna be an auto grader for this project?
No.
No. Just asking.
Yeah, you're used to knowing it's correct by writing your own. All right, no questions? All right.
Not yet.
Not yet. All right. So I'm not going to be able to get to lab 7 today. So we'll go ahead.